Good morning, everyone. Welcome to Tech, AI, and Beyond. Thank you so much for joining us today. Now, in our last deep dive, we talked all about the incredible advancements in generating clean power, solar, wind, you name it. And that's fantastic, right? But it's really only half the battle. Generating that power is one thing, but getting it where it needs to go, that's a whole other challenge. And it's the crucial next step we're diving into today.
So, here's the core of the problem. Our current electrical grid. Look, it was an absolute marvel of 20th century engineering, no doubt. But it's an antique now. It's an analog, one-way system that was built for a world of a few massive, predictable power plants. Today, it's being slammed with a 21st century reality, a world of decentralized, fluctuating, and multi-directional energy. You've got solar on roofs, wind farms. It's a fundamental mismatch. So the solution isn't just a simple upgrade, it's a total, ground-up reinvention. And that reinvention has a name: the smart grid.
All right, so here's how we're going to break it all down today. First, we'll really dig into the problem in the grid's analog crisis. Then we'll start building the solution, layer by layer, starting with the hardware in the digital nervous system, and then the intelligence, the grid's AI brain. After that, we'll see how you, yes you, fit into this picture as consumers become grid partners. We'll look at how this all leads to building a resilient future. And finally, we'll tie it all together with the smart energy payoff.
Okay, let's jump right in with Section 1, the grid's analog crisis. To really get why the smart grid is such a massive leap forward, we first have to get our heads around the old system it's replacing, its architecture, and maybe more importantly, all the critical, deep-seated flaws that come with it.
Think of the old grid like a one-way street. It's really simple. You have a few huge power plants at one end, and they just push electricity down a single path to millions of us, the consumers, at the other end. And for its time, it was a brilliant design. But today, we need a dynamic, digital network, kind of like a complex city grid with traffic flowing in every direction. Power from our rooftop solar panels needs to flow back to the grid. Energy from our EVs might need to flow back into our homes. This bidirectional flow is the core architectural challenge we've got to solve.
And these old design principles lead to some really crippling problems. First, there's basically no visibility. Utilities are flying blind. A lot of the time, they only know there's an outage when people start calling to complain. Second, it's wildly inefficient when it comes to handling peak demand. Third, because it's so centralized, it's dangerously vulnerable to these massive cascading failures. And finally, its entire structure is just fundamentally incompatible with renewables. Seriously, it's like trying to manage all the traffic in a bustling modern city using nothing but a paper map of the major highways. You're completely blind to what's actually happening on the ground.
And this is the terrifying real-world consequence of that vulnerability. The 2003 Northeast blackout is just a perfect, chilling example. It all started with a single equipment failure at a plant in Ohio. Just one. But because the system was so blind and interconnected, it triggered this massive, unstoppable chain reaction, a cascade that ultimately plunged 50 million people into darkness across the US and Canada. It was a brutal lesson in how one tiny problem can explode into a multinational catastrophe.
Okay, so let's talk about that inefficiency. It all boils down to this one concept: peak demand. The entire grid, every wire, every transformer, has to be built to handle the single moment of highest electricity use for the entire year. Just think about it, that one scorching hot summer afternoon when every single air conditioner is cranked to max. It's exactly like building a massive 10-lane highway just to handle 1 hour of rush hour traffic every day, and then letting it sit mostly empty for the other 23 hours.
And this number, well, it really drives home just how wasteful that brute force approach is. See, to meet that very brief peak, utilities have to build these special power plants called peaker plants. These are often expensive, they're often polluting, and they might only get turned on for a few dozen hours in an entire year. So for up to 99% of the time, this massive expensive investment is just sitting there completely idle. We're talking about a system that is intentionally, massively overbuilt, and that is incredibly costly for everyone.
But honestly, the biggest challenge of all is the old grid's total incompatibility with renewables. You've got two main problems here. First, intermittency. The grid was designed for steady, predictable power from a coal plant. It doesn't know what to do with the fluctuating output from solar and wind. Then you've got the bidirectional problem, right? When thousands of homes are generating their own power from solar panels, any extra energy has to flow backwards onto the grid. The old equipment just wasn't built for that. It turns millions of us into what are called prosumers. We both produce and consume energy. And that's a new reality the old one-way street grid just can't handle. So, the big question is, how do we fix all this? Well, that brings us to our second section, the digital nervous system. Look, if the old grid is basically blind and unresponsive, the very first step is to give it senses and motor functions. We're talking about deploying a whole new generation of smart, digital hardware across the entire network, giving it the ability to collect data and, crucially, to control itself.
And really, at the heart of this new nervous system is the smart meter. This is the device that replaces that old spinning analog dial on the side of your house. It's not just a meter, it's a digital two-way communication hub. It's constantly sending detailed usage data to the utility, and it can receive information back from them. This one change instantly enables things like remote outage detection. But even more importantly, it's the key that unlocks all the cool dynamic pricing and demand response programs we're going to get into in just a bit.
Now, out on the big, high-voltage transmission lines, we need even more sophisticated sensors. These things are called phasor measurement units, or PMUs. The absolute best way to think about a PMU is like an EKG for the grid. It takes this incredibly high-definition snapshot of the grid's electrical health, its voltage, its frequency, up to 120 times every single second. This gives grid operators, for the first time ever, a real-time system-wide view of what's happening. It lets them spot dangerous instabilities and stop those cascading blackouts before they even have a chance to start.
And this is where it gets really cool. When you combine all these sensors with automated switches and controls, you create what's called a self-healing grid. So picture this. A tree branch falls and takes down a power line. On the old grid, your lights are out and they stay out until a crew in a truck can physically get there. But on a smart grid, sensors instantly detect that fault. An advanced software system analyzes the data and boom, it automatically tells switches to reroute power around the problem area. The outage is completely isolated, and for most people, power is back on in seconds. A lot of the time, you wouldn't even know it flickered.
Okay, so we've given the grid a nervous system. It can feel things now. The next logical step, we have to give it a brain. Welcome to Section 3, the grid's AI brain. I mean, the sheer volume of data flying around a smart grid is it's impossible for any human team to process in real time. This is exactly where artificial intelligence becomes absolutely essential. AI is what turns that massive flood of data into predictive, actionable intelligence. And one of the most critical jobs for AI here is forecasting. Think about it. By sifting through just massive amounts of data, we're talking historical usage, weather patterns, economic activity, you name it, AI can predict electricity demand with incredible accuracy. But what's maybe even more important, it can predict the output from renewables. AI can analyze satellite imagery of cloud cover or run complex wind models to tell you what your solar and wind generation is going to look like hours or even days in advance. It effectively makes the unpredictable predictable. And hey, this isn't just some abstract theory. Take this powerful case study from Google's DeepMind. They pointed their machine learning algorithms at their own wind farms. And get this, it allowed them to predict power output 36 hours in advance. The result? Well, you can see it right here. This newfound predictability increased the economic value of their wind energy by about 20%. That is a massive, game-changing improvement just from being able to see the future more clearly. And if you want a massive, real-world example, just look at California. Their grid operator, CISO, has to manage one of the largest renewable portfolios on the entire planet. And every single day, they face this thing called the duck curve. It's this infamous chart that shows a huge dip in demand from the main grid in the middle of the day, because solar's flooding the system, and then an incredibly steep ramp-up in demand as the sun sets and all that solar disappears. The only way they can manage this huge daily swing and keep the lights on is by relying on sophisticated AI and automation. Honestly, California is like a living laboratory for the future of the energy grid.
All right, this next section, this marks a really fundamental shift in thinking. Section 4 is all about how consumers become grid partners. The smart grid is set to completely change our relationship with energy. We're going from just being passive takers to becoming active participants in keeping the grid balanced. And the key concept that makes this all possible is called demand response.
The whole thing is enabled by those smart meters we talked about because they allow for dynamic pricing. The idea behind these time-of-use rates you see on the chart here is super simple. The price you pay for electricity changes depending on how much demand there is on the grid. So as you can see, power is cheap overnight when demand is low. That's off-peak. But it gets really expensive in the evening when everyone gets home and turns everything on. This creates a really powerful financial incentive for all of us to shift our energy use, like, say, charging an electric car, to those cheaper off-peak hours.
But the true power of demand response, that really gets unlocked when you bring in automation. We're talking about all the smart devices in our homes that can automatically respond to signals from the grid. Think about it. A smart thermostat can pre-cool your house an hour before the peak price hits and then just coast through it. A smart EV charger can automatically wait until 2 a.m. to start charging when power is cheapest and cleanest. Even a smart water heater can heat up its tank in the middle of the day when solar power is everywhere and practically free.
Okay, now imagine this. You take thousands or even millions of these smart devices, you aggregate them all together, and you control them with intelligent software. When you do that, you create what's called a virtual power plant, or a VPP. This isn't a physical building, it's a distributed network of devices. But acting together, a VPP can provide gigawatts of flexible capacity to the grid almost instantly. It literally turns our collective energy demand from an unpredictable problem into an incredibly valuable grid balancing asset.
You know, all this amazing technology also makes our grid way more secure and robust. And that's going to be our focus here in Section 5, building a resilient future. Because the smart grid isn't just about being efficient, it's about creating a piece of critical infrastructure that can actually withstand modern threats, everything from extreme weather events to sophisticated cyber attacks.
And a really key tool for building that resilience is the microgrid. You can think of these as self-sufficient local energy islands. So imagine a major hurricane comes through and knocks out the entire regional power grid. Well, a hospital that has its own microgrid, maybe with solar panels and batteries, can just island itself. It disconnects from the broken main grid and just keeps operating independently. This is absolutely critical for making sure essential services stay online when we need them the most.
But of course, there's a flip side to all this digitization. While it brings these incredible benefits, it also creates a vast, new attack surface for cyber threats. I mean, let's be real. A grid that's connected to the internet and controlled by software is a potential target for malicious actors, and securing it has become one of the most critical national security challenges we face today.
And there's no single silver bullet for this. Securing the smart grid requires a multi-layered strategy, something experts call defense in depth. What does that mean? Well, it means hardening the physical devices themselves with strong encryption. It means continuous AI-powered monitoring to spot threats in real time. It demands super strict supply chain security to make sure hardware isn't compromised before it's even installed. And of course, it means constant training and drills for the human operators, so they're always ready to respond.
Okay, this all brings us to our final section, which is really the culmination of all these technologies. Section 6, the smart energy payoff. So let's take a moment and summarize the really compelling benefits that we get from building this digital energy future.
First and foremost, the smart grid is just vastly more efficient. It cuts down on energy that's just lost as heat in transmission lines, it empowers all of us to use energy more wisely, and critically, it helps reduce or even eliminate the need for those incredibly wasteful peaker plants that just sit idle 99% of the time. And at the end of the day, less waste means lower cost for all of us. Second, it is so much more resilient. Those self-healing capabilities we talked about, they dramatically reduce the length and the scope of power outages. Microgrids make sure our most critical facilities stay powered no matter what. And a really robust cybersecurity strategy hardens the whole system against modern threats. It's a grid that's actually built to withstand the shocks of the 21st century.
And finally, the smart grid is more flexible. And you know, this is arguably its most important quality. Its ability to seamlessly manage two-way energy flows and to use AI to balance that fluctuating generation from renewables, that is what truly unlocks the full potential of clean energy like solar and wind. To put it simply, a future powered by renewables is just not possible without a smart grid to support it.
And that really is the ultimate takeaway. This isn't just about cool tech for the sake of cool tech. A smarter grid means less wasted energy, it means lower costs for everybody, and it means a more reliable and secure power supply for a world that is becoming more and more dependent on electricity every single day. So, to wrap it all up, the transition to a smart grid is really just as fundamental as the shift we all made from a landline to a smartphone. It's about building a new digital foundation for our energy system, a foundation with a nervous system of sensors, an intelligent AI brain, and a new set of rules that transforms all of us into active partners in our energy future. Now that we have a solid understanding of how we can generate and deliver clean power, our next deep dive is going to explore where we actually use most of it. So I hope you'll join us next time for Blueprint for Tomorrow, Building Sustainable Cities. Thank you so much for watching. If you enjoyed this, please subscribe, like, and share, and don't forget to hit the bell for more from Tech, AI, and beyond.